Hello. We're running this lecture again after some spotty internet issues earlier today. So, this is a redo of the 18 1, our first lecture for Physics 192. So, before we dive into this too much about what we've got on the slides today, I did want to give kind of a brief overview of what we're going to cover in the course. So, the first third of the course or so, quarter to a third of the course, is all going to be based on thermodynamics, right? And then moving on from that, we've got kind of our chemistry, thermodynamics, but chemistry and physics side of that. We're going to be diving into electricity and magnetism. And at the very end of the semester, we might see a little bit of relativity. That remains to be seen if we've got a definitive. If we've got enough time for that, I'd love to do it at the very least as some bonus lectures where we can discuss some of those really fun things. It's really just kind of cool stuff that I want to share with you guys, if nothing else. But thermodynamics is kind of a broad topic to say the least, and we're not going to dive into it too much in depth in this course. There might be a lot of things that you might have seen in another course before, especially if you've taken chemistry recently. A lot of these details and these concepts might be something that you're pretty familiar with at this point. But there's kind of a lot that you can expand into on that one. If you've got different majors that have your own thermodynamics courses, then you're going to end up kind of going into a particular side of that thermodynamics. Physics has its own 400 level thermodynamics where we talk about things maybe a little bit differently than the engineering majors do, a little bit differently than the chemistry majors do. So everyone's going to have a little bit of a different take on thermodynamics if you end up needing that in your major. For a lot of people, this might be kind of covering the basics of the topics, and that's it, and that's all you'll need. But anyways, what is thermodynamics? Let's kind of break apart that word for a minute, and probably both of these things are things you've seen before at this point, right? Thermo, well, we recognize thermo is thermal, something to do with heat or temperature. Dynamics, our good friend, right? Movement. That's what we see in that one. And in a poor way of saying things, it's a lot of small things moving very fast, right? And moving in every which way is really also kind of an important point here. We'll discuss that in detail. Before we get into that, though, let's talk a little bit about matter as a whole, right? Not just gas particles move around like in this, but the different phases that we might see matter taking. So, what you're probably pretty familiar with, what I'm made out of, as far as I'm concerned, are solids, right? The things that are rigid that we experience. So these are items or objects that have strong structure between the atoms, right? So if I'm thinking about something like a crystal shape or a metal that is solid, what we actually see if we zoom in really, really, really far is that all of those atoms are in some very nice grid-like structure. And all of the atoms in that grid-like structure are interacting with each other, and they're pulling and they're pushing on each other, and they're staying right exactly where they are, right? Think about what happens if you think to something like the hydraulic press YouTube channel, right? Where they take all sorts of crazy things, put it under a hydraulic press, and pure experimentalism, what happens? There's a lot of neat things that we can actually see in that, and I love to watch the different shapes expand out and everything else like that. There's a certain joy in watching things explode. But there's some really cool things that happen there as well, right? So for the most part, what we see is that all of these objects are a pretty definitive shape. And the hydraulic press only really changes that shape because, well, it's a crazy amount of force, right? It's a very strong structure with a lot of force behind it that's pushing into this object that's what it takes to actually deform a lot of these solid objects. Now, I'm sure you know different solids have different amounts of force that it takes to reshape them. But the important thing is that I can't take a sheet of paper and stretch it out into a really large sheet, right? I can't take a rock and compress it down into a tiny pebble, right? The only way to really do that is to smash it apart, which is certainly not just compressing it in place. So most solids, as we're going to describe them, are incompressible, right? Like nearly truly, they are incompressible. Now you can argue that there's a little bit that you could do depending on what solid you're looking at or something like that. But if you look at any of those, so let's make that reference back to the hydraulic press channel. If you look at something when they do like a block of metal or steel or something like that, what actually happens there is that the metal itself isn't being compressed. The metal feels that force and it buckles outward, right? It expands into this massive pancake shape. So the metal itself is not able to be compressed. It's still going to take up the same amount of volume, even if we deform it, even if we bend it up every which way. Where the matter actually is, that volume that it's taking up by being there isn't going to change. Now, if we take a solid and we add a lot of heat to it, what we're going to get is the next phase, liquid, right? And this is our first, what we call a fluid. So, for example, I've got my handy dandy objects here on the side. If we look at something like this, typical household window cleaner, right? This is a fluid, and we can see it sloshing around there, right? It's kind of neat because what's going on in here is that the atoms are no longer rigid like they would be in the solid, but they are still pretty close together, right? They're still interacting constantly. There's a lot of stuff going on between the atoms, and for that reason, they're not just filling up the entire thing. They're holding shape to a certain degree, right? And when I say holding shape, they're not just filling the top of this thing. They will change to fit the structure of the container that they're in, and that is a feature of fluids, but they're not expanding to fill the entire container. The volume that it's going to take up is going to be a constant no matter what happens. And again, like solids, they are mostly incompressible, right? We're not going to think about circumstances where they are compressible. That's one of those kind of specific cases. To a very small degree, some of these things are, but it's not for our interest to talk about that too much. The main takeaway here is that both solids and liquids are very nearly completely incompressible. Now, let's take a liquid, let's add some more heat to it, and what do we get? The next phase of matter, gas, right? And this one's a little bit unique because now instead of the atoms interacting constantly in this large grid structure, or maybe they're just kind of passing by, but they're still interacting, gases have a lot less density to them than the other two phases. And when they're like that, the atoms or the molecules, whatever particles that it takes to make up this gas, they're no longer constantly interacting. In fact, we kind of idealize them that they're not really interacting that much at all. There's only really going to be one time that they're going to interact, and that's if two particles end up colliding midair, right? And I'm saying midair, but it is the air, right? That's the idea here, is that these particles are actually what makes up the air. For the most part, the interactions between the atoms are almost non-existent except in collisions. They're separated far enough apart that there's no real constant forces that are acting between them, unlike in solids and liquids. In solids and liquids, we've discussed how even when we were talking about something like the normal force or friction, that's really a result of atom-atom interaction from the electromagnetic force, right? And we're going to get to that. That's its own chapter. But it's actually a part of a fundamental force. We just don't see it on that real day-to-day kind of scale, right? We don't look at what atoms are doing on a day-to-day scale. We're instead seeing the result of all of these atoms together. So again, looking at all of these atoms together, there's not going to be any large binding force acting between all of those gas particles. And because of that, because there is so much space between all these particles, we end up being able to actually compress gas fairly well, right? You've probably got a can of compressed gas somewhere in your house right now. Let me pull out my second fun example for the lecture. Something like this, right? Household duster or anything else like that. Any sort of aerosol can is actually a container of compressed fluid. And I'm going to be a little bit weird with my wording there because I don't know how well you can hear that sound, but there's a little bit of shaking going back and forth inside of this thing. There's some sort of liquid in here. And the reason that there's a liquid is because this container is actually under a whole lot of pressure, at least on the inside. All of that pressure on the inside is actually compressing a gas so far that it turns into a liquid. And if you've got a can of compressed air or something like that at home, I'd suggest you try this thing. But when you actually end up releasing it, let me get this on camera. Right, you can see there's a little spurt of gas that actually comes out. Even though it's liquid inside, once that pressure is released, it goes back into a gas, but feel the can afterwards. It's kind of a neat effect, but if you let loose one of these things for long enough, you'll actually feel the can getting colder as all of the energy is starting to leave as the gas is released. It's kind of a neat thing, but it's something that we'll talk about a little bit later when we can get into it in a little bit more detail. So, gases are compressible. They will take the shape of a container, and not only will they take the shape of a container, they will expand to fill it. Liquids will take the shape of a container, but will stay within their own volume. They're incompressible. They're going to maintain the volume that they've got. Solids will maintain their same volume, but they're also not going to rearrange themselves when they're inside of a new container, right? If I launch a spaceship out into outer space, it's not going to suddenly expand to fill all of the space. It's going to stay in that exact same shape that we set it up with, right? Now, on the far end of these things, if you're looking at these, we've got plasmas. If you add more and more heat to a gas, you end up with a plasma, and that's where electrons actually dissociate from the atoms that they came from, and you've got this nice soup of a bunch of ions. That's not something we need to worry about. On the very far end, on the other side, we've got Bose-Einstein condensates. We typically just call those either condensates or BECs. But those are typically, I think the warmest BEC is typically somewhere around 10 microkelvin. So about 30,000 times colder than space or so, right? Give or take a little bit there. But they're incredibly cold. They have a lot of crazy features to them where, kind of the quantum mechanics side of things starts to take over. And it's a really cool thing, but it's pretty far outside of the scope of the course right now. But if you're interested in it, I highly recommend looking into some of the experiments and the cool things we can do with BECs. We've even got one lab that's working with them here at Miami. So they're really cool things. So, how are we actually going to end up talking about these things? Well, let's say that we've got some sort of system, right? And we're talking about some sort of system. I'm talking about some sort of container filled with maybe gas or something else, right? We'll end up dealing with a lot of gases, but we will talk about some of the others as well. But if I've got my sort of container of gas, there's some different features that we could talk about of this container, right? And I don't want to talk about the container itself. I want to talk about what's inside the container. So inside the container is what we call the system. That's all of the particles that make up this whole thing. And the gas in my system, it has a mass, it has a volume, it has a pressure, it has a temperature. And all of these values, what they're doing is they're describing what state the gas is in, right? If we change the temperature, we change the state of the gas, right? Not necessarily changing the phase. It's always, it stays the same phase, but the state of that gas might be changing. And so we call these naturally state variables. Right? Now, for some of these things, we will also have mass density, which is something that we've seen before, I think. We've got kilograms per cubic meter, which is just talking about how much mass can I pack in a certain volume. So you might notice here that when I'm talking about something like state variables, I'm not talking about any single one atom inside of that container. Something like that can of pledge, that might have something 10 to the 24th, 10 to the 25th atoms, right? Any number bigger than 10, physics usually gets kind of unhappy about, right? It's too many things to keep track of, realistically. So instead, we don't worry about every single individual atom. We instead think about the ensemble of atoms, how they're all acting together. And how they're all acting together, that's where we pull these values from, right? What volume do all of the atoms take up? What's the combined pressure from all of the atoms bouncing around? What's the average temperature of all of these particles? And then finally, of course, what's the mass when I sum up all of those particles? But none of those things are concerned with a single atom of the ensemble. Everything is just kind of lumped together as one big value. So let's take a practice with this definition. The first problem we've got here, we want to find the diameter of a copper sphere that has the same mass as a 10 by 10 by 10 centimeter cube of aluminum. So, if you are working on this thing, if you haven't worked through this problem already, I highly recommend pausing the video somewhere around right here. Please do work on it by yourself. I am going to run through the solution, but this is for your practice. So give it an honest try, and then, come back and watch this and see how you did. Or maybe you got stuck somewhere, watch this a little bit until you figure out what gets you unstuck, and then pause again, try and finish out the problem. It is in your best interest to try and solve the problems now. But anyways, let's go ahead and work this one out, right? So let's come up with some things here. Let's draw ourselves a very bad cube. For example, we'll have something like that. Ooh, it was almost a cube. So there is our cube of aluminum, and we will have a sphere of copper, right? We like some visual aids to help us out here. Now, as I'm looking at this thing, there's a couple different things that I'm looking for. Let's list out the things that we're actually given. We know we are dealing with aluminum. And so if we look at that table, which you can find in the textbook, by the way, that is not some hidden value that we're trying to keep from you. We've got mass density of an aluminum, so rho of Al is equal to 2,700 kilograms per cubic meter. The mass density of copper is 8,920 kilograms per cubic meter. And then we're also given that we are looking at something that is, let's call it a side length L. L is 10 centimeters, right? Volume is L cubed. Some details that we've got there. Let me rewrite that actually. There we go. So, as we're approaching this thing now, we're trying to figure out, okay, well, this has some mass, call it capital M. This has the exact same mass, capital M, right? We know those two things are equal. So let's think about what the definition of mass density actually is. Whoops. Try that again. Mass density is equal to the mass divided by the volume that it's taking up. So if we know these two things are supposed to be equal in each case, then what we're really saying is that the mass density aluminum times the volume of aluminum must be equal to the mass is equal to the mass density of copper times the volume that the copper takes up. Right? So far, so good. We don't really care what this M actually is. You know, it would be nice to know, I guess, for some purposes, but I'm not super concerned about it. I'm actually a lot more concerned about finding the volume of this copper because we're looking for the radius of this sphere, or rather the diameter of this sphere. So if we can find the volume, we know that that volume right there is going to be a 4/3 pi r cubed. Right? That's how we're really getting there. We're looking for what that V is supposed to be, and then finding the radius is just another step away from that. So let's solve this thing out for that. Let's say we have mass density of aluminum times volume of aluminum divided by mass density of copper, because those are both values that we've got. The volume of the aluminum is the only thing we don't have a value for yet. All of this is equal to the volume of copper. I'm not going to plug that thing in yet. I'd rather just find this value first. It's a little bit easier for me. So the only thing we really need to do here is we need to find what this volume of the aluminum cube is, right? And I want you to be careful here. We need to keep track of units. And if that wasn't true last semester, it certainly is this semester, right? Last semester, we had a little bit of leeway with some of our units sometimes. You could, come back and correct things later. But here in thermodynamics, our units are going to be changing, and they're going to be very, very, very important to keep track of, right? We're going to have a lot of different units to keep track of, so I want to get you started on this early. I see we have kilograms per cubic meter. I see a length of centimeters. Not so good. That's not going to match. So let's convert this instead to be 0.1 meters, right? And now that means that the volume of the aluminum, and let's label that, volume aluminum is equal to L cubed. That means we have 0.001 cubic meters. We have a value for aluminum. We have a value for the volume of aluminum. We have a value for the density of aluminum. We have a value for the density of copper. Let's go ahead and solve out for this volume of the copper sphere. Right? And when we plug all of that stuff in, Let's see. I should have wrote down that value ahead of time. Let's solve it out real quick and see what we get here. 2,700 times 0.001 divided by 8,920. We should end up with something like 3.027. Pardon me. 3.027 times 10 to the negative fourth cubic meters. Fantastic so far. Now we just need to take our volume equation. Let's do a little bit of quick rearranging on this thing. Let's say, okay, well, the volume of copper times 3/4 times 1 over pi. Let's take the cube root of all of that stuff. And that should be equal to our radius, right? When we plug all of that stuff in, we should be finding something like 0.0416 meters. We want the diameter, so we're one step away. We say, okay, well then the diameter is just going to be 0.0833 meters, right? Or let's call it centimeters, just for fun. 8.33 centimeters. To put it back into the units as compared to what we've got. Right? And let's think about that for a minute. Let's think about what these numbers actually mean. We had an aluminum cube, and we've got a smaller copper sphere. It's not even as wide as our aluminum cube. Not to mention that we're essentially, lopping off all of the corners. It's not taking up that much volume, but compare those densities, right? Aluminum is a very, very, very light metal. That's why it gets used a lot in like professional bikes and a few other applications. It's just so incredibly light that it's very useful. For things where you need the strength of a metal, but you can't afford to have that much weight. Copper, on the other hand, doesn't get that same use, right? It's got a lot more weight to it. It's got some other properties, though, that we use it for other things. It doesn't have the same purpose of aluminum, but it's a lot more dense as a metal. And so we would expect, okay, if we want these things to weigh the same, they're probably going to have to be different sizes. That makes sense. So this answer, to me, seems pretty reasonable. So let's go ahead and go back to our slides here because we've got another problem, and this one's going to come in a few different parts here, right? We got some things going on with this one. So the first part of this problem is kind of separated away from the second half, but I do want to provide a little bit of context for this while we're talking about it. So if we're thinking about something like the nucleus of a uranium atom, I want you to pause right there for a second. Think about an atom, right? I think we talked about this a little bit when we were talking about quantum mechanics. There used to be this old, really, really cool website. It's not up anymore, not the original website at least, but it asked the question, what if an electron was 1 pixel large on your computer screen? How big would the proton have to be to make a hydrogen atom? And how much space would you have to put between those two to actually realistically represent the space in a hydrogen atom? And it was incredible because what you end up with, think about how large a single pixel is on your screen. You had to do 3 miles of scrolling to go from the electron to the proton. It's a huge distance. It is a crazy large distance, right? If you remember the chemistry, the gold foil experiment where we discovered the atomic nucleus and we said definitively there's a small positively charged nucleus. Most of the particles that we threw at that thing, they passed right on through because there's a lot of empty space, right? There's actually very little space that's realistically taken up inside of the atom. Most of it's empty space. You've got a nucleus that contributes most of the mass, and then you've got the electrons way on the outside. And there's electrons way on the outside. That's where all of the interaction happens through the electromagnetic force. So you don't have a bunch of things actually compressing that atom because essentially everything's going to be happening at that boundary of where the electron is at. So let's contextualize that in the question again, right? We're looking at only the nucleus of a uranium atom. So almost all of the mass of the atom, but cutting away all that extra empty space. I want you to think about what that might mean for our answers, right? All of these things, all of these densities, these are taking into account all of that extra space, right? When I'm looking at a big block of copper, there's still all of that empty space in between the atoms, or rather, in between the nuclei of the atoms, right? The atoms are as tightly packed together as they can get. So when we find our answer here, expect it to be much, much larger than any of these values that we see in this table. So let's go ahead and start with that part of the problem, and then we'll look at the second part about the neutron star right after that. So let's get ourselves a little bit more space here. Somewhere right there. We are looking at whiteboard 18-2. So if we are looking for the density of this thing, the first thing that we're going to do, if you've ever seen any of the pictures that we have of atoms, and we're not going to be able to ever see an actual atom, right? But we can get pictures that kind of represent what that would look like. And there it is. Physics' best friend, the sphere. Right? We're just going to assume that this thing is a sphere. That's going to make our life a lot easier to deal with here. So what we have on this thing, the other hint on this is that if you look, we have a diameter. Anytime you see diameter, that's either a circle or a sphere, right? Right there. That should be your keyword. So we know that this thing has a diameter. Let's go ahead and mark this in a couple different places. It has a mass, first, of 4 times 10 to the negative 25th. That's pretty tiny. Kilograms. But then it's also got this diameter of 1.5 times 10 to the negative 14th meters. Right? Also ends up being pretty tiny lengthwise. So we're looking for this density. So we say, okay, we need a mass density. That is rho is equal to m divided by the volume that it gets taken up. Right? We have a diameter. We need to convert that into a volume. We're going to go back to our volume of a sphere equation. V is equal to 4/3 pi r cubed. And we say, okay, well, diameter, that is just twice the radius, right? So we can convert that value pretty readily here. And what we should end up finding, we plug in these values. We've got the mass straight out. We've got the volume that we can plug in. When we plug all of that stuff together, it's mostly a calculator problem for this one. We should find something like 2.26 times 10 to the 17th kilograms per cubic meter. Okay, so 10 to the 17th, that's really the kicker here. And let's go back to our table real quick for a quick comparison. It's not a comparison, right? It's a huge difference. It's a huge difference. That empty space really does contribute a lot. That's really what this comes down to. But it's kind of a neat thing, right? There's a lot of neat stuff that actually goes on when you start to pick apart what's actually inside of the atom and what does it actually take to make up some sort of solid. You know, what are all these interactions? Where are they coming from? Right? There's a lot of fun questions to ask like that. So one thing that I would like to point out while we're on this value or something else, if you're doing any of these problems yourself, normally we have some things that go on when we're in class or anything like that. In a normal semester, we would at least. If you have slight differences in how you rounded numbers or anything else, we might have slightly different numbers. You might have 2.25 or 2.27, right? If there are small differences like that, I'm not at all worried about it. Everything should be totally fine. Maybe you rounded somewhere differently than I did, right? I'm not going to be claiming that I'm the best with keeping track of every single decimal that's actually important. Sometimes I lop off some numbers somewhere. So as long as you're getting a close number, the concept and working out the equation is the most important part, right? So I'm not going to be super concerned if you've got it one way or the other, even if you're answering this stuff in Canvas. As I've got it set up in Canvas, anytime you're putting in a numerical answer, that's all going to buffer to it. So as long as that buffer's in place, you're not going to need to worry about any of that stuff. So let's go to the second part of this problem, though, and let's think about what goes on with this. So talking about something like a neutron star. A neutron star is made of neutrons, right? And maybe some protons scattered in there, but for the most part, let's say just nucleons, right? So if this thing is all nucleons, it's kind of like the biggest atom, right? It's not acting like an atom in a traditional sense because of the temperature, and there's a few weird things going on with this. But essentially, the neutron star is so incredibly dense, and there's such a force from the gravity that the space between nucleons and atoms breaks down, and you end up pulling everything in anyways, right? Just like the uranium nucleus. So here's what we're going to do. We just found what the mass density of the nucleus is. So that's a bunch of nucleons bundled together. So let's say we expand that. We make that ball of nucleons much bigger, say the size of a neutron star, for example. We can assume that that mass density is going to be exactly the same. So let's kind of abstract this a little bit more now. Let's get back to the problem. Let's say, okay, let's imagine we've got a thimble, that little tiny thing that helps cover your finger. That's got about 2 cubic centimeters worth of space in it, right? Let's say we took that thing, we scooped up a little bit of neutron star in it. How heavy would that be? Would you be strong enough to lift it? Let's find out. So we already have the density, and in fact, we also have the volume, right? So let's separate this out into a new color. So we're going to say thimble of neutrons. So we've got this new volume. Let's call it V of T for V of thimble. And this is equal to 2 cubic centimeters. And again, we immediately see some sort of problem. That's cubic centimeters. We have meters. We need to make sure that these things match each other. So what I'm going to do is I need to convert this volume into cubic meters. Now, be careful with this one. This is not 0.02 cubic meters, right? I need to convert centimeters 3 times because it's centimeters cubed. If I have something like this, I could define this as 0.02 centimeters squared times meters, but that's pretty ugly. And that really doesn't help us because now it's even more confusing, right? So let's say no to that one. Let's instead just say, okay, well, I know it's going to be essentially V of T is equal to, I'm just going to rewrite this so I got a little bit more space here. And what I'm going to do to convert this, I'm going to say, okay, well, there are, in every 1 meter, there are 100 centimeters. And I need to convert 3 of them. That's a nice, easy way to do that I think helps kind of explain that a little bit better. So what we end up with is 2 times 10 to the negative 5th cubic meters, right? That decimal spot's going to move over 6 times. And now that we've got this volume, what we're going to do is we're going to try and find what the mass of these neutrons is actually going to be. Mass of the neutrons that we've got now, this is going to be equal to rho times V. What we should end up finding... Oh, whoops. I had my value scrolled in the wrong spot. Oh, whoops. 0.2 times 10 to the negative 5th, if we'd like to do that. But it should be 10 to the negative 6th. I'm sure you guys will catch me on that when we do this live. But if we actually convert that into a mass, what we should find is something like 4.5 times 10 to the 11th kilograms. Let's do some quick comparisons here real quick. We've got something 10 to the 11th. Okay, the Earth is still a little bit bigger than that. The Earth is on the order of 10 to the 24th. So it's still got a few of those, right? So maybe that's not a fair comparison. I was hoping we'd find a really neat number there. But anyways, still a pretty tiny amount, right? It's not going to take that many to make up the mass of the Earth. But let's go back into this problem here real quick. So we're almost there. We've got the mass of this thing, and we recognize that this is probably going to be pretty heavy. But remember, what is weight? It is not a mass. It's a force. It's a force acting on a mass. So weight, call it capital W, is going to be equal to, Classic, say it with me, mg, right? Our good friend gravity's back. 9.8. So we can say, okay, take this mass, multiply it by 9.8, and we should end up with something like 4.4 times 10 to the 12th newtons. And I realize that's a pretty large number, and we don't really think about that many things in newtons. So this is roughly 10 to the 12th pounds. So, heavy, right? I think that's fair to say. So, let's keep moving on for now. Let's talk about mass and another value you might have heard at this point, moles, right? I'm going to start with this, and I'm just going to say, okay, well, we can measure mass in grams or kilograms, right? Our standard unit's kilograms, but for just a little while, I'm going to talk about grams. Instead of talking about this in terms of mass and grams, though, I could talk about maybe the number of particles that are actually inside of my system. Right, I was talking about the 10 to the 24th, 10 to the 25th atoms that I might expect to see in that can of aerosol, right? We can talk about that the same way. We can do that with any system. It's a really big number. It's not practical to always talk about all of them. I'm probably not going to get an exact number. I mean, let's be realistic here, but I can get a pretty good number about how many there would be. And let's call that value capital N, right? N for integer numbers. So if we know that the total mass of the system is capital M, and we know that there are a number of particles, capital N, then we can create this relationship between the two that says, okay, well, the total mass of the system is equal to the number of particles we have times the mass, lowercase m, of each particle. Okay, well, that works, and, well, we've got a good idea of what that mass of each particle should be, but it is still pretty tiny. Right, 10 to the negative 25th kilograms. But that's okay. And while we're at it, we can also define a number density, which is why I keep specifying mass density as rho. Mass density is kilogram per cubic meter. Number density is number per cubic meter. But number isn't really a unit in its own sense. So sometimes we call it just per cubic meter or 1 over cubic meters. Sometimes I like to write number per cubic meters because it reminds me that it's a number density. That's what helps me at least. We've also got this neat equation right over here that the number density is equal to the mass density divided by the mass per particle. That's a fun little relationship that you can get by plugging this equation in to what we had for the mass density. So that's a good value to have. We've also got another value that you might have heard of, moles. Right? How many moles of a substance do you have? And this is a pretty specific value, actually, and it's kind of a unique one. Avogadro's number doesn't show up in nature in the same way as a lot of these other things might. This is a value that we picked specifically. Right? The idea here is that we have picked an Avogadro's number to say that if we have an Avogadro's number of particles, then if we were to take the atomic mass of any value, we would get exactly that value in grams. Right, so for example, it's a little bit clearer with an example. If I have helium, that has 4 nucleons, 2 protons, 2 neutrons. If I have 1 Avogadro's number of helium atoms, so 1 mole of helium, I would have 4 grams of helium. It's very useful in that sense. If I look at something like water, H2O, that has 18 nucleons. 1 mole of water is 18 grams. It's a nice quick conversion, and then that's why we've picked this exact number. So to get that number, to find the number of moles that we have, we take the number of particles that we currently have divided by Avogadro's number, this 6.02 times 10 to the 23rd, where it's, again, number per mole is really what that value is, or just per mole. So, and here's kind of saying, in a similar sense, what part of that is. That value that I'm talking about, the mass of 1 mole of a substance, is what we call the molar mass. Right? So that molar mass, when we're talking about something like helium, the molar mass of helium is 4 grams, which is essentially just converting the atomic mass into grams, right? And that's a 1 mole mass. This extra divided by 1,000 if you'd like to convert it to kilograms instead of grams. But I find it's usually easier to just think about it in grams and then convert to kilograms afterwards, right? But this is a different way if you haven't seen this before, if you don't have already a method solidified when you're looking at this stuff. So this also gives us another definition of how we can talk about the number of moles. You can take the total mass of all the particles divided by the molar mass, and that tells you how many moles you've got. And then just for reference down here at the bottom, 1 atomic mass unit is equal to 1.66 times 10 to the negative 27th kilograms. If you'd like to do that conversion, check the number for yourself. Okay, so we've got our last whiteboard problem here. We're looking for the number density of these two materials. So let's kind of work on this one. We've got some values here. We've also got some atomic mass numbers, and we'll need both of those. So let's give ourselves a little bit of space here. And I'm actually going to solve this problem generically at first. I'm not going to define which material I'm solving for before I actually solve it, because what we'll find is that by the end of this thing, all we really need to do is plug in numbers. So let's think about the things that I'm given first. Let's give ourselves a little bit of space here, separate that out. Whiteboard 18-3, what we end up seeing here is we've been given essentially pick one of the metals, right? If we pick one of the metals, then what we end up knowing is the mass density of that metal, and we also end up with the atomic mass, capital A, right? That's how many nucleons are in the average particle. And chemists are going to scream at me, but you can take any of those values you see for atomic mass, and just like we've got in this table, don't worry about the fact that it's, oxygen is something like 16.995 or 15.995. Don't worry about it. Just round it up to 16, right? I'll deal with the hate mail for that one. It's significantly, just use an integer value. Okay, but anyways, if we pick either of these materials, then what we're going to end up with is knowing the mass density and the atomic mass of that material. So we want to use that to find the number density, or N over V. Okay, so let's try this. We know that the mass density, that's defined as the total mass divided by volume. And here's where we start to run into an issue immediately. What volume are we talking about? We don't really have one, right? They don't specify any sort of volume. They don't specify any sort of system. What we do know is that we're dealing with a solid, and a solid is incompressible. So that's more or less saying that the lead over there is going to be the same as the lead over there. It's going to be the same as the lead over there. Or more specifically, it's going to have the same mass density no matter where I'm looking, right? If I have a really big sample, if I have a really small sample, and if the density is going to be the same, then I can argue, well, the number density ought to be the same too, right? So I'm not going to try and specify any sort of one value. Instead, what I'm going to do is more like a dimension analysis on this. So we say, okay, well, rho is equal to m over v. That's great, but well, the v is actually kind of nice, right? Because we see we're looking for that. So v already being on the bottom of this fraction is okay. So it's really m that we have to worry about. And we think, okay, what can I do with that? I need to find some way that I convert that mass into a number. Well, if I look back at my slides, you might remember that mass is equal, the total mass of the system is equal to the number of particles times the mass per particle. Okay, well, that's getting somewhere. But how do I know what the mass per particle is? Right? It changes because the number of nucleons between every atom is different. Well, that's okay because we're given how many nucleons each material has. Right? That's the value A that we're given. So we can take that and we can take that a step farther and say, okay, well, that's probably going to plug into there. But to plug into here, we need that the mass is equal to the number of nucleons times the mass of each nucleon. And if you've been messing around with this a little bit, you might notice that the mass of a single nucleon is the inverse of Avogadro's number. So we plug in all of those things. Right now what we end up with is rho is equal to n, capital N, times A times 1.66 times 10 to the negative 27, all divided by V. Remember what we're after here. It's this, right? There's some extras that come along with that. So let's move everything that's not N over V over to the other side. When you move that stuff over, what we should find is something like rho divided by A times 1.66 times 10 to the negative 27th, right? And now we're in a golden spot because we know what rho and A are for each material. So we can go back to that slide. We can look at that table. We can say, hey, starting with aluminum, I see aluminum on this thing is 2,700 kilograms per meter cubed. I see aluminum on this thing has 27 nucleons to it. I can plug in those values. And if I do that for aluminum, I should end up finding something like 6.02 times 10 to the 28th, let's say, number per cubic meter. For lead, that's going to be something more like 3.29 times 10 to the 28th. Just by plugging in at the very end like that. Very nice and easy. Well, at the very end, right? The rest of that solving, there's a little bit to do in that one. It's a little bit strange, I realize. So let's go on to the very end here. And we're going to kind of take a little bit of a historical perspective on this thing. And I'll kind of talk you guys through this as we go through the different pieces. Thermodynamics is kind of cool because it's still part of what we call classical physics, right? So this was before quantum mechanics. This was before relativity, where we still thought we understood the world. But we saw what was going on with things like gases, and we were trying to understand how all these things related together, right? And so what we actually did to develop a lot of these laws and equations is we made a lot of observations. We ran a lot of experiments. We said, okay, let's take this, container full of a gas. Let's put a fire beneath it. Let's add a bunch of heat to it. What happens? And through making all of these different observations and very careful measurements, we came up with these different laws kind of in an empirical fashion, right? It wasn't a bunch of abstract solving before we actually came up with these things. So, and what we are left with is essentially what we call the 3 laws of thermodynamics, and then the 0th law kind of gets tacked on there as well as a little bit of an extra. We'll end up talking about all of these individually and give it a little bit more of a rigorous definition. But for now, I'd like to make the joke kind of about what each of these things are and how you can see that if I take a glass of wine, say that's a low entropy system, it's pretty well ordered. I smash that on the ground. I ruin the party, as I always do. It's pretty easy for the universe to let the glass be shattered in every which way and to see the wine spilled everywhere, right? Think about how easy that is to happen. Somebody accidentally knocks it over, somebody throws it, somebody does all sorts of things. There's a lot of options that can shatter that glass. Think about the likelihood that the universe is going to put that back together and get all the wine back inside. Tipping the glass was a very easy process, right? You went from low entropy, very well ordered, to a very high entropy, very low order, very chaotic. The universe likes to increase that entropy, and that's kind of what we see within the 2nd and 3rd laws. But again, all of these things are things that we're going to talk about in a little bit more detail. They're going to get each their own little section as we go forward in these next few chapters on thermodynamics. But it's fun to talk about these things a little bit now to give you a little bit of an overview of what we're going to see in the future. Anyways, that's going to conclude our first lecture for now. We'll have this posted up, and hopefully, if everything works out, the next one will be live. So I'll see you again then.